Okay, in lesson 1, exercise 14A.1 and 2, we became more familiar with the idea of a rate of change between two variables being equivalent to the slope of the graph between the two. We had the two scenarios where we had a straight line with a constant slope. So no matter where you drew the triangle to measure rise over run on the graph, you would get exactly the same value. And then we worked out that if we want to find the average rate of change or the average slope, we can take the chord, make a chord, and find the rise over run of the chord. And the rise over the run and the slope would depend entirely on exactly which chord was drawn. So we needed to be very careful. What we're having a look at today is instantaneous rates of change. And the reason that we do that is because they tell us significantly more about a situation than the average rates of change do. So for example, if you were driving to Harndorf, which is about 40 kilometres away, your displacement time graph might look a little bit like this. So let's say you start at your house, and so this is going to be time and this is going to be distance from your house, where this is 0 and this is 40, which is where Harndorf is. So we start at your house and we drive a certain speed. In fact, we're going to drive a little bit slower. So a slow speed means a shallow steepness or a shallow gradient. Then we stop at a set of traffic lights for a couple of minutes. Then we go again a little bit faster this time, so a steeper line. We stop for morning tea for a little while. And then we go a little bit faster again, stop at the lights right before the highway, and then we're onto the highway driving quite fast. You can see that the steepness of the graph is a measure of how fast we're going, because it's a change in our distance with respect to time. The steeper the graph, the faster you're driving. Now, the police don't care how long it takes you to get there. They don't care about your average speed. They don't care how many times you stopped along the way. What they care about is your instantaneous speed at any given point. So really what the police are interested in is how steep is this section of the graph, and was it of a higher value than the speed limit? So out on the freeway, our speed limit is, let's say, 100. If your graph, your distance time graph, shows a steepness or a gradient that's higher than 100, then you must have been speeding. Now, that's relatively easy to calculate on a very artificial distance time graph or displacement time graph like we've got here. We can calculate the gradients of each of these sections and work out what they are in terms of the change in distance per time. And then we can work out whether you were or were not over the speed limit for those sections. Things get significantly more complicated though when we've got a curved graph. So for example, if I wanted to know the slope of the graph at x equals 3, I could draw a chord to give me an estimate. Now, if I draw a chord from 0 to 3, then that is going to give me a terrible estimate of the slope at 3, isn't it? The slope at 3 is quite clearly negative. The chord is quite clearly positive, so they're not even the same sign. So then we do this, we make a slight change, and let's draw a chord from 1 to 3. So this time it's negative, so it's at least a better estimate. It's still not a fantastic estimate because we've got this big region of deviation in here. So let's make the chord even smaller still. Let's make the chord between 2 and 3. So we can draw, and you can see now that the deviation of the function from the chord is getting smaller and smaller, which means our chord is a better and better estimate. Let's go one step further. I have the advantage of being able to zoom in. Let's go one step further and draw our chord between, let's say, 2.6 and 3. And you can see that that again is another step towards a better estimate. Hopefully it's become apparent to you that the best estimate that we're going to get for the slope at the point 3 is the chord that is the shortest. So we could put our chord at 2.8 and have a nice small chord there. 2.9 gives us an even smaller chord. we could make our distance, our difference between 2.9 and 3, which will give us an even better approximation. It doesn't take much thinking to go, well, why don't we just make the distance 0? Let's just make it the point on itself. If we do that, we end up with the situation where the rise is 0 and the run is 0, because we're talking about the same point. That means our slope is going to be 0 divided by 0, which is undefined. So we can't actually make the difference between the 2 points 0 because of this undefined. What we do instead of making the difference between the two 0 is we use a tangent. So we use a straight line that touches the curve at a single infinitesimally small point. Here we go. Here's the tangent here. Now, I just eyeballed that, and unfortunately that's all there is to it. And you should be able to see that there's really a couple of degrees of variation that I can put that will change the slope ever so slightly. Unfortunately, we are limited to eyeballing it and working out which tangent looks like the best tangent.